This is the fact file for 2.4 alkenes. So in this topic, you need to be able to define the term unsaturated hydrocarbon and explain why alkenes are described as unsaturated. Recall the qualitative test for alkenes using bromine water. Use sigma and pi bonds to explain the relative bond strength and relative bond length of the carbon-carbon double bond. Recall that the double bond is a centre of high electron density, and use this to explain the difference in reactivity of alkanes and alkenes. Describe the catalytic hydrogenation of alkenes using finely divided nickel. Describe the reaction of chlorine, bromine, hydrogen chloride and hydrogen bromide with alkenes. Define the terms electrophile and heterolytic fission. Recall the mechanism of electrophilic addition between chlorine, bromine, hydrogen chloride and hydrogen bromide with alkenes using curly arrows. Explain with reference to the stability of the carbocation intermediates involved, the formation of major and minor products during the electrophilic addition of hydrogen bromide to unsymmetrical alkenes, and finally describe the addition polymerization of alkenes, for example, ethane and propane. So, alkenes are unsaturated hydrocarbons, and that means they contain at least one double bond or a triple bond. So they contain a carbon-carbon double bond as their particular functional group, and they're named according to IUPAC rules. You select the longest chain of carbon atoms containing the double bond, place the ending "ene" on the basic name, number the chain starting from the end nearer the double bond, and use a number to indicate the lower number of the carbon attached to the carbon-carbon double bond. And as in alkanes, you prefix with substituents, so side chain positions are based on the number allocated to the first of the carbons in the chain with the double bond. So for example, we have ethane, 2 carbons, propane with 3 carbons. There are no numbers involved here because there's no other places that the double bonds could be. We have pent-2ene, and it could either be pent-1ene or pent-2ene, but in this case it's between the second and third carbons that we have the double bond, so it's pent-2ene for the smaller number. And then we have 5-methyl-hex-2ene. So if we count the chain here, 1, 2, 3, 4, 5, 6, so it's 6 carbons long. And then we have the methyl group on this one, which would be the 5th. We're counting from this end because that gives us the smallest number where the double bond is, and the methyl group then is attached to the 5th carbon here. So the double bond is comprised of a sigma bond and a pi bond. And a sigma bond is a covalent bond formed by the linear overlap of atomic orbitals. A pi bond is a covalent bond formed by the sideways overlap of p orbitals. So the pi bond is slightly weaker than the sigma bond, and it's easier to break as a result. So this makes alkenes more reactive than the corresponding alkanes, and makes their chemistry more varied and interesting. So the double bond is an area of high electron density, and species attracted to such areas are known as electrophiles. So examples of electrophiles include halogens and hydrogen halides, and these react with alkenes by adding to the double bond, resulting in new structures. So for example, ethane reacts with bromine and with hydrogen bromide to give bromoalkanes. So in the case of the reaction with hydrogen bromide, it's 1 bromoethane if we start with ethane, and there's just 1 bromine in the product. With bromine, you end up with 2 bromines in the product, and that would be 1,2-dibromoethane because 1 adds to each side of that double bond. And the use of bromine solution is a diagnostic test for the alkene functional group, as the yellow, orange, brown bromine water decolorizes in the presence of the double bond. Electrophilic addition of HBr to an alkene such as ethane involves a 2-step reaction mechanism. So in the first step, the HBr molecule, which is polar, acts as an electrophile and attacks the pi bond in the ethene molecule. An electrophile is an ion or molecule that attacks regions of high electron density. So in the second step, the carbocation intermediate is attacked by the bromide ion to complete the addition. If we have a look at that mechanism here, we can see the two steps. So in the first step, the bond is giving electrons to the hydrogen end of the hydrogen bromide, and the electrons from the hydrogen to bromine bond are going to the bromine. So we end up with the bromide ion here and the carbocation. The electrons go from the bromide ion to that positive carbon, and we end up then with our bromoalkane here as the product. So if you have unsymmetrical alkanes such as propane, the mixture of major and minor products is formed, and this is due to the nature of the carbocation intermediate produced. So we have three types. We have primary, which is a carbocation which has one carbon directly bonded to the positively charged carbon. We have secondary, which has two carbon atoms directly bonded to it, and tertiary, which has three carbon atoms directly bonded to that positively charged carbon. So the secondary carbocation is more stable than the primary, as the methyl group can help to stabilise the positive charge. So in the case of a primary carbocation, the two hydrogen atoms offer no such stabilisation. And if we look at this example then, the major product in this case is going to be 2-bromopropane. And there's the longest chain there, 3 carbons, that's propane. And here it's going to be 1-bromopropane. And the reason for that is in the first example here, we have a secondary carbocation. You see here that carbon is joined to 2 other carbons. And in the second example, the positive carbon is just attached to 1 other carbon. So alkenes can be converted to alkanes in the presence of hydrogen gas using a finely divided nickel catalyst, which just means that it's in a very thin layer. And it's an important reaction in the production of margarine and other soft spreads from vegetable oils. And our equation for it here is we have ethane plus hydrogen with a nickel catalyst, and we just write that above the arrow, gives us ethane. So alkenes are also used to produce plastics by a process called addition polymerization. So polymerization is the joining together of many small molecules or monomers to form a large molecule. And a polymer is a large molecule formed when monomers join together. And monomers are many small molecules which join together to form a polymer. So ethane is used to produce polyethane, the polymer used in plastic bags. And we can write this as an equation. So we draw the monomer. You see we do the 2 carbons with the double bond here written horizontally, and then whatever the other groups are around it. N shows that there are a large number of those molecules involved, and then we do square brackets to show that that is the monomer. When we draw the polymer, we just draw the repeating unit, and you'll see here that the 2 carbons remain where they were. The groups around the carbons are the same, and we draw 1 bond out each side showing that the molecule continues, and then the square brackets show that that is the repeating unit, and N tells us that it's repeated many times, the same number of times as whatever the number is in the first part of the equation.